Hi, in this video, I'm going to discuss a question in electricity. Okay, so it looks very simple circuit for five different resistors are connected as shown in the diagram. The question is find the equivalent resistance across points A and B. That's the question. Okay, so normally when you get a question like this, students normally they try to find out, or whether they'll try to find out whether are there any resistors connected in series. You know, when they are connected in series, we can add their resistance to find the equivalent resistance. Or if they are connected in parallel, you can find the equivalent resistance by using 1 over R equal 1 over R1 plus 1 over R2 and so on, right? Okay. So normally when students see this type of circuit, they will try to find out whether they are connected in series or parallel. Are there any components here? All five are resistors. Whether they are connected, are there any resistors connected in series or parallel, right? We'll check one by one how 1 ohm and 4 ohm are connected. You know, when you are saying two components are connected in series, you know the condition. There should not be any junction or branch between those two components, is it? Then we can say they are connected in series. When you are saying two components or more than two components connected in parallel, they should be directly connected across two junctions. Okay, based on that, we will check whether any of those components are connected in series among them or whether they are connected in parallel among them. One by one, we will check it. 1 ohm and 4 ohm, are they connected in series? No, because there's a junction here. So 1 ohm and 4 ohm are not in series. Same way, 1 ohm and 3 ohm are not in series because there's a junction. If there's a junction between two components, then certainly they are not in series. Same way, 2 ohm and 5 ohm, they are not in series because there's a junction. Same way, 3 ohm and 5 ohm, not in series. There's a junction. 2 ohm and 3 ohm also not in series because there's a junction. So we can't solve any of those two resistance of resistors by considering they are connected in series, because none of them are connected in series among them. Okay, we will check whether any of those two or more than two resistors connected in parallel. You know, if you are saying two or more than two components connected in parallel, then they must be directly connected across two junctions. Okay, when you think about 1 ohm and 3 ohm, they are connected to this junction directly. You can see this junction directly, but 3 ohm is connected to this junction, but 1 ohm is connected to this junction. So they are not in parallel because they are not directly connected across two junctions, right? Then only we can say they are connected in parallel. Same way when you think about 2 ohms and 3 ohms, 2 ohm is connected to this junction, one terminal of 2 ohm, one terminal of 3 ohm, also connected to the same junction, but the other terminal of the 2 ohm is connected to this junction and the other terminal of the 3 ohm is connected to this junction. So 2 ohm and 3 ohm also not directly connected across two junctions. Same way if you check other components also, other resistors also, none of them are connected in parallel. So we can't solve them by using the equation 1 over R equal 1 over R1, 1 over R2. We can't solve it. So none of them are connected in series among them. None of them are connected in parallel among them. Okay, so how are you going to solve this circuit to find the equivalent resistance? We can find it. Okay, so none of them are connected in series or parallel. So we are going to use Kirchoff's first law and second law here, right? So we are going to use Kirchoff's first law and second law to solve this circuit to find the equivalent resistance across A and B. Kirchoff's second law is used in Edexcel Cambridge and IB, but little harder question this one, but you can understand this. Okay, you know Kirchoff's first law says that SUM, you know, the addition of the current approaching a junction is equal to total amount of current leaving the junction. You know that is the Kirchhoff's first law. Kirchhoff's second law says in a closed circuit or in a closed loop, sum or the addition of the total EMF will be equal to sum of the potential across the components in that closed loop. We know that, right? So in a closed loop, when you consider if there is no power supply, then the EMF of that closed loop will be taken as 0. That is the Kirchoff's second law says that. And normally we take the EMF, the direction, in a power supply, current always flows from higher potential to lower potential. So we normally take a power supply, if the voltage, the EMF of the power supply, if it is 4 volt, we say the direction of the EMF is out of the positive terminal. That's the way we take it. EMF will be out of the positive terminal. That's the way we take it, because always in an external circuit, if we consider this component here, the 4 volt is the EMF, means we consider the EMF in this direction, because current flows from high potential to low potential, right? So we are going to use that method to solve and find the equivalent resistance across A and B. We are going to use only the Kirchhoff's first law and second law. We can't use normal method by considering series connection, parallel connection won't work here, because none of them are connected in series or parallel among them. In any textbook, you can see how to use the Kirchhoff's second law. We normally define a direction of the loop. So first I consider this closed loop. I'm going to consider this one. If I want, I can name that loop. Already AB is there. I can call it C, this point D. So this I can say E, F, G, H. Right. So I'm going to consider this closed loop. Before that, the EMF of the cell is not given. I don't need it now. Later I need it, but I just take it as EMF as I can say epsilon. The current coming out of the power supply is also not given. I can take it I. The current coming out of the power supply, I can take it I. Okay, at this junction, according to Kirchhoff's first law, the current will split, right? So I can say the current through 1 ohm is I1. Current through the 2 ohm will be the current I will split here at this junction. So current through 1 ohm is I1. So current through the 2 ohm will be I minus I1. Right. I can take other way also. Current through 2 ohm I1, then current through 1 ohm will be I minus I1. I can take either way, no problem. I just took it. Current through this one is I1. So current through this one is I minus I1. Kirchhoff's first law I am using it. Okay. Now when this current goes here, it can split here, or maybe this current can split here. So I don't know whether this current is splitting here or this current is splitting here. I don't know. But finally, I am taking like this. No reason. I am taking like this. This I1 is splitting here as I2. And through this one, the current is I1 minus I2. Current through this one is I1 minus I2, because current through 1 ohm to the junction C is I1. So at junction C, this current will split and flowing through this I2 and flowing through this one I1 minus I2. I'm just taking it, right? So then what I'm taking, the current flowing through this one, the 3 ohm is I2. This current I minus I1, both will rejoin at junction D and flow through 5 ohm as they will be added here I2 plus I minus I1. So that will be I minus I1 plus I2. Say I'm using the Kirchhoff's first law. Nothing wrong. If you want, you can take this way. Current I minus I1 is splitting here as I2. Then this will be I minus I1 minus I2. So I2 is flowing this way. You can take the current through 4 ohm as I1 plus I2. Nothing wrong. You can take it that way also. Nothing will go wrong, right? So I took it like this. So current through this one is I minus I1 plus I2. You can see now here at this junction. So these two currents will again rejoin. I1 minus I2 plus I minus I1 plus I2. If you add this current and this current here, you will again get I. That means the current going to flow through the B to the power supply again I. So Kirchhoff's first law is working perfectly. Right. Now I'm going to use the Kirchoff's second law. When we are using Kirchoff's second law, we need to consider a closed loop in a particular direction, either clockwise direction or anti-clockwise direction. Either way, we can take it, right? So I can take it either clockwise direction or anti-clockwise direction when I'm using Kirchoff's second law. So if I use Kirchoff's second law in this direction, I'm going to use it in clockwise direction. Okay, in this closed loop, I'm considering this closed loop. I'm considering the closed loop E, C, D, F, E. So that's the closed loop I'm considering. So Kirchhoff's second law says total EMF in that closed loop is equal to total potential across the components. So in that closed loop, there are no power supply. So total EMF will be equal to 0 in that closed loop. So total potential across the components are going to be across this one, current is flowing in this direction from left to right. The loop also taken that way. You can see the loop. So that will be I1 into 1. Here I2 into 3. The potential across this one. Current flows from high potential to lower potential. But here when you consider the loop is, I took it in clockwise direction this way, current is flowing opposite direction. So it should be taken as minus time 2 into I minus I1, right? So here when I use the Kirchhoff's second law in this closed loop, sigma E, the Kirchhoff's second law, normally they say sigma E is equal to sigma IR. You can see in any textbook, sigma IR. That is total EMF is equal to total potential across the components. That's the way Kirchhoff's second law is used in all textbooks. Right, so now I use this here. Sigma E, so here the total EMF in this closed loop is 0. So I1 into 1, that is 1 into I1 plus 3 into I2 here, 3 into I2. Here current is flowing from left to, but I'm taking clockwise direction, so it's opposite direction. So minus 2 into I minus I1. So I found total potential in this closed loop is equal to total EMF, but there are no power supply, so EMF is equal to 0. So solve this one, I1 plus 3I2 minus 2I plus 2I1 equals 0. Solve it further. It's going to be I1 plus 2I1, 3I1 plus 3I2 equal to, bring it to the right, 2I. Take it as first equation. Take it as first equation, right? So now I'm going to use the Kirchhoff's second law again for this closed loop, C, G, H, D, C. In this closed loop, I'm taking again in clockwise direction. Okay, can't I take it in anti-clockwise? Yes, I can, no problem. But I am taking in clockwise direction. If you want, you can take it in anti-clockwise direction. No problem, nothing will go wrong. Right, okay, so if I use the Kirchhoff's second law in this loop, like C, G, H, D, C, in clockwise direction, I'm taking it clockwise direction. So here also I can take clockwise direction. So total potential 4 into this current is I1 minus I2. This direction is opposite. This current is opposite. So minus, here it will be minus 5 into I minus I1 plus I2. Here also, when I consider clockwise direction, this current is opposite to my clockwise direction. So again, minus 3I2 equal to 0 because in that closed loop, there is no power supply. So total EMF will be equal to 0. So solve this one. 4I1 minus 4I2 minus 5I plus 5I1 minus 5I2 minus 3I2 equal to 0. So 4I1, 5i1, 9i1, minus 4i2, minus 5i2, 9i2, minus 3i2, minus 12i2. Here 5i, when you take it to the right side, it will become plus 5i. You can take it as equation 2, second equation. Right, so I need to solve these two to find the I1 and I2 in terms of I. So I is taken as the current coming out of the power supply. So I need to find I1 and I2 in terms of I. Okay, how can I solve it? Multiply this first equation by 3, so I can get 9i1 again. So 1, the first equation into 3 gives 9i1 plus 9i2 equal 6i. Take it as third equation. Okay, so 2 and 3 simultaneous equations. I can solve them. I can solve by subtracting second equation from third equation. I will get it. 9i1, 9i1 will get cancelled. So 9i2 minus 21i2 equal to I6 minus 5, 1. So I2 will be equal to 1 over 21i. I found the I2 in terms of I. So I can substitute this in first equation to get the I1 in terms of I. So use this, substitute this in first equation. So 3 times instead of I1, yes, 3I1 plus 3 into, instead of I2, I can say 1 over 21i is equal to 2i. Solve it and find the I1. You know how to solve it. So then you take it to the other side. You can solve it. So when you solve it, you'll get I2 will be equal to, I1 will be equal to, you will get it 13 over 21 I. I2 equal, we already found it, 1 over 21 I. So I found I1 and I2 in terms of I. Simple maths, but I found it, right? Still, I don't have the answer for the question. Question is, what's the potential across, what's the resistance across A and B? Okay, so you know that if I think about this whole, for the whole network or this resistance network, equivalent resistance is R. That equivalent resistance R must be connected across AB. So I need to take one more equation in terms of EMF. So for that, I'm going to use the Kirchoff's second law again for the loop. I'll consider this point as P. If I name this point P, so I'm going to consider a loop from P, A, E, C, G, again P. That closed loop. I'm going to use the Kirchoff's second law. Can you see that? From P, A, E, C, G, B, P. In that closed loop, I'm going to use the Kirchoff's second law again. So I'm going to use the Kirchoff's second law again in clockwise direction. For the loop, I'll use black ink for that. P, A, E, C, G, B, P. For this one, I'm going to use in clockwise direction. Closed circuit. You can see it's a closed circuit. Any closed circuit I can select. Any closed circuit I can select when I'm using the Kirchoff's second law. Right. So in that closed circuit, there is EMF. I took it as epsilon. There's a power supply. I took it as EMF of that power supply epsilon. So when I consider that, the total potential across this one is I1 into 1 ohms. So 1 into I1 in this one. Then 4 into plus 4 into I1 minus I2 current through this one. right? In this closed loop, these are the only two components in this closed loop. Can you see that? In that closed loop, those are the only two components. So potential across this one is 1 into I1. Potential across this one is 4 into I1 minus I2 is equal to total EMF epsilon. I take it as EMF this one. Okay, substitute I1 is equal to 13 over 21 I. Instead of I1, I am substituting plus 4 into I1 minus I2. You can see that I1 minus I2, I'll find it here. That's easy. I1 minus I2, if I find it here, that will be 13 over 21 minus 1 over 21. That is going to be 12 over 21I. So I can substitute 12 over 21I here. 12 over 21I equal to EMF. Solve it. So here 4 into 20, 13 over 21I plus 48 over 21I equal EMF. Solve this one. That's going to be 61 over 21I equal EMF. Okay, so I am going to find EMF over I. What is it? EMF over I. Imagine the circuit. The equivalent resistance of this connection of resistors, if I take it as R, you can see this is the R. This is A. This is B. Connected across the power supply like this, EMF. Can you imagine that? Across A and B, the whole equivalent resistance of this network, if I take R, the EMF is E, the current coming out of that cell, I took it as I. So the equivalent resistance R is equal to EMF over I. EMF over I gives the resistance of this equivalent circuit. That is the equivalent resistance. So from this equation, if I find EMF over I, that is the equivalent resistance of this circuit. So from this one, I'm going to find EMF over I, that is equal to 61 over 21. That is going to be 2.90 ohms. So the equivalent resistance of this whole circuit is 2.90 ohms. The reason I'm telling it again, EMF over I is the equivalent resistance. You can imagine the equivalent circuit. So here EMF over I is the equivalent resistance which is connected across A and B. So EMF over I is 61 over 21, that is 2.90 ohms. That is the equivalent resistance of this circuit. I hope you understood the method. Not easy. There are mathematics, simple maths. We are using algebra, mainly simultaneous equations.